Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, and your mind is still churning with thoughts and worries. Or maybe you're the kind of person who finds peace in understanding the hidden workings of our world. Either way, you're exactly where you need to be. Tonight we're going to drift through one of the ocean's most fascinating yet invisible features. We're going to explore the thermocline, those hidden boundaries of warm and cold that divide the seas into distinct worlds. Layer upon layer, temperature zone upon temperature zone. You don't need to do anything but rest. Let your breathing slow, your muscles soften, and your thoughts begin to float. We have all the time in the world to wander through these liquid borders, these thermal frontiers that shape everything from the tiniest plankton to the largest whales, from ancient submarine warfare to the future of our warming planet. Before we begin our gentle descent through temperature and depth, if you find these ocean stories soothing, consider subscribing so you don't miss future journeys into the blue. And if you're still awake enough, I'd love to know where in the world you're listening from tonight. Now let's slip beneath the surface and discover the invisible architecture of the sea. The ocean doesn't reveal all its secrets at first glance. From above, from a boat or a beach or a clifftop overlook, the water appears as a single continuous body, perhaps rippling with waves or glinting in sunlight, but fundamentally unified in its blueness. Yet beneath that deceptive surface uniformity lies a world divided. The ocean is not one temperature from top to bottom. It is not mixed evenly like a giant bathtub where warmth spreads uniformly throughout. Instead, the ocean is layered, stratified, separated into distinct horizontal zones where temperature changes dramatically over just a few meters of depth. These zones are separated by boundaries, transitions so sharp and so persistent that they function almost like invisible floors and ceilings in the water column. These boundaries are thermoclines, from the Greek words meaning heat and slope, and they are among the most important yet least visible features of our planet's oceans. Imagine for a moment that you could see temperature. Imagine the ocean rendered in colors not of blue and green, but of warm reds and oranges near the surface, fading to cool blues and deep purples in the depths. If you could see the ocean this way, the thermocline would appear as a dramatic band of rapid color change, a vivid stripe where the palette shifts abruptly from warm to cold. This invisible boundary isn't just a curiosity for scientists. It shapes where marine life can thrive, determines how nutrients flow through the water, influences the behavior of sound waves traveling through the sea, and even plays a role in weather patterns and climate systems. Understanding thermoclines means understanding one of the fundamental organizing principles of ocean structure, one of the hidden rules that governs life in the sea. The discovery of thermoclines came gradually, through centuries of maritime exploration and scientific curiosity. Sailors and fishermen had long noticed that water temperatures could vary, that certain fish preferred certain depths, that the ocean seemed to have different characteristics at different levels. But it wasn't until the age of systematic oceanography that scientists began to understand the layered nature of the sea. One of the great milestones in this understanding came during the voyage of HMS Challenger, a British research vessel that circumnavigated the globe from 1873 to 1876 in what became the first truly comprehensive scientific survey of the world's oceans. During the Challenger expedition, scientists made thousands of measurements of ocean temperature at various depths. They lowered thermometers on long cables, carefully recording the readings as they brought them back to the surface. What they found astonished them. The water wasn't gradually getting cooler as they went deeper. Instead, there was often a layer where temperature dropped precipitously, where just a few dozen meters of descent could mean a change of several degrees Celsius. This wasn't random variation. It was consistent, predictable, a fundamental feature of ocean structure. They had discovered the thermocline, though they didn't yet use that exact term or fully understand its implications. As oceanography advanced through the early 20th century, researchers developed better instruments for measuring temperature profiles. The bathythermograph, invented in the 1930s, revolutionized the study of thermoclines. This device could be lowered through the water column on a cable or even dropped from ships and aircraft, recording a continuous graph of temperature versus depth on a smoked glass slide as it descended. For the first time, scientists could see the shape of the thermocline clearly, could measure its depth and strength, could map how it varied from place to place and season to season. Naval forces quickly recognized the military significance of these temperature boundaries, and bathythermographs became standard equipment on submarines and surface vessels during World War II, used to predict where submarines might hide beneath acoustic shadows created by the thermocline. Today we understand thermoclines as natural consequences of the way the ocean interacts with sunlight, wind, and the physical properties of water itself. But even with all our modern instruments and satellites and computer models, thermoclines retain an air of mystery, invisible boundaries that we can measure and predict but never quite see with our naked eyes. They are felt rather than seen, experienced as sudden cold when diving deeper, or detected as zigzag lines on fish finders and sonar screens. They are barriers and pathways, obstacles and opportunities, dividing the ocean into distinct ecological realms. To understand how a thermocline forms, we need to think about what happens when sunlight strikes the ocean surface. The sun is the ultimate driver of almost everything that happens in the upper ocean, and thermoclines are no exception. When sunlight penetrates the water, most of its energy is absorbed in just the first few meters. The ocean surface acts like a solar collector, soaking up heat during the day and warming considerably. This heat doesn't spread evenly down through the entire water column. Water is an excellent absorber of light, particularly in the infrared wavelengths that carry heat energy. Within the top meter or so, the majority of solar energy has already been captured by the water molecules. By 10 meters down, almost all the red and infrared light has been absorbed. By 100 meters, even the blue and green wavelengths that penetrate deepest are largely filtered out. This means the upper layer of the ocean gets warmed by the sun, while the deeper water remains cold, insulated from the heat above by the very water that absorbed the sunlight. But here's where things get interesting. Warm water is less dense than cold water. When water molecules warm up, they move faster, vibrating and jostling in ways that cause them to take up slightly more space. The water expands ever so slightly, becoming lighter, more buoyant. This warm, buoyant water wants to stay at the surface. It doesn't sink because it's lighter than the cold water below. This creates a stable situation where warm water sits atop cold water, separated by a transition zone where the temperature changes rapidly. The transition zone, the thermocline itself, forms because of this density difference. The warm surface water and cold deep water don't want to mix. They're separated not by any physical barrier, not by a membrane or wall, but by their own physical properties, by the simple fact that dense fluid sinks and buoyant fluid rises. The thermocline is the region where this transition happens, where temperature and density change rapidly over a short vertical distance. It's a gradient, a slope of temperature, and it can be remarkably sharp. In some tropical waters during calm conditions, you can descend through a thermocline that drops 5 or 6 degrees Celsius in just a meter or two of depth. That's an extraordinary temperature change concentrated in a very small space. But the surface layer of the ocean isn't perfectly still. Wind blows across the surface, generating waves and creating turbulence. This wind energy gets transferred into the water, stirring and mixing the upper layer. The mixing is powerful enough to distribute heat downward, creating what oceanographers call the mixed layer, a zone typically 50 to 100 meters deep where the temperature is relatively uniform because the water is constantly being churned by wind and wave action. The mixed layer sits atop the thermocline, a well-stirred zone of relatively warm water overlying the rapid temperature drop below. Beneath the thermocline lies the deep ocean, a vast realm where temperatures are cold and stable. In most parts of the ocean, deep water temperatures hover just a few degrees above freezing, typically between 2 and 4 degrees Celsius. This cold water fills the abyssal plains and deep trenches, making up the vast majority of the ocean's volume. It's cold because it originated in polar regions, where surface water cooled until it became dense enough to sink, then flowed along the ocean bottom toward the equator in the slow circulation patterns that connect all the world's seas. The thermocline then is the boundary between the warm, sun-warmed, wind-mixed surface layer and the cold, still, ancient water of the depths. The strength and depth of a thermocline vary tremendously depending on location and season. Not all thermoclines are created equal. In fact, oceanographers recognize several different types of thermoclines, each with its own characteristics and lifetime. Understanding these different types helps us appreciate the dynamic, ever-changing nature of ocean temperature structure. The permanent thermocline, also called the main thermocline, is a relatively stable feature found in the open ocean. This is the thermocline that persists year-round, separating the surface ocean from the deep ocean across vast stretches of water. The permanent thermocline typically extends from about 200 meters down to roughly 1,000 meters depth, depending on location. Within this zone, temperature drops from perhaps 15 or 20 degrees Celsius at its upper boundary to just a few degrees at its lower boundary. The permanent thermocline exists because of the fundamental difference between sun-warmed surface water and deep water that originated in polar regions. It's a feature of the ocean's large-scale structure, shaped by global patterns of heating and cooling, by the circulation of water masses across thousands of kilometers. The permanent thermocline is strongest in tropical and subtropical waters, where the surface ocean stays warm year-round and the contrast with deep water is most pronounced. In equatorial regions, you can find yourself swimming in bathwater, warm surface water above a thermocline that drops to near freezing temperatures just a few hundred meters below. This creates an intense thermal gradient, one of the steepest temperature transitions found anywhere in nature. The tropical permanent thermocline is a formidable barrier between the warm upper ocean and the cold abyss. But the ocean isn't just characterized by this one permanent feature. Superimposed on top of the permanent thermocline, in the upper reaches of the water column, we find the seasonal thermocline. This is a shallower temporary thermocline that forms during warmer months and disappears during colder months, particularly in temperate regions where the seasons are pronounced. The seasonal thermocline forms in spring and summer when increasing sunlight and weaker winds allow the very uppermost layer of the ocean to warm considerably without mixing deeply. In spring, as days lengthen and the sun climbs higher in the sky, the ocean's surface begins to absorb more heat. At first, the entire mixed layer warms together, stirred by winds that keep it relatively uniform. But as summer approaches and winds calm, solar heating can warm just the top few meters more rapidly than mixing can distribute that heat downward. This creates a sharp seasonal thermocline, often found between 10 and 50 meters depth, above the permanent thermocline deeper down. During summer, temperature profiles in temperate oceans can show multiple thermoclines, step changes in temperature at different depths, like terraces on a hillside. The seasonal thermocline represents some of the most stable water conditions of the year. With warm, light water stacked atop cooler water, the ocean becomes stratified, resistant to vertical mixing. Nutrients that have been used up in surface waters can't easily be replenished from below because the thermocline acts as a barrier, preventing deeper, nutrient-rich water from mixing upward. Similarly, oxygen that's abundant in the surface layer can't easily reach deeper waters. This stratification has profound effects on marine ecosystems, concentrating biological activity in certain zones and leaving others relatively barren. When fall arrives and days shorten, the seasonal thermocline begins to break down. Solar heating diminishes and winds strengthen, stirring the surface layer more vigorously. The surface water cools, becoming denser, and begins to sink. This destroys the stratification that characterized summer. The seasonal thermocline disappears as the upper ocean mixes deeply, erasing the sharp temperature gradients. By winter in temperate regions, the mixed layer can extend to great depths, sometimes several hundred meters, homogenizing the upper ocean into a single cold, well-mixed zone. Then, when spring returns, the cycle begins anew, and the seasonal thermocline forms once again. In addition to permanent and seasonal thermoclines, there exists an even more ephemeral feature called the diurnal thermocline. This is a thermocline that forms and disappears on a daily basis, driven by the day-night cycle of solar heating. On calm, sunny days, especially in tropical waters where sunlight is intense, the topmost meter or two of the ocean can warm significantly during daylight hours. This creates a very shallow thermocline right at the surface, where the water warmed by the day's sun sits atop cooler water just below. The diurnal thermocline is incredibly fragile. Any significant wind or wave action will destroy it by mixing the surface layer. And at night, when the sun sets and the ocean begins to lose heat by radiation to the atmosphere, the diurnal thermocline disappears as surface water cools and mixes downward. The diurnal thermocline is rarely more than a meter or two thick, but it can be remarkably strong when conditions are right. Temperature differences of 2 or 3 degrees Celsius concentrated in just the top meter of water create measurable effects. Satellite sensors measuring sea surface temperature can detect the difference between daytime and nighttime temperatures caused by the formation and destruction of this daily thermocline. For marine organisms living right at the surface, The diurnal thermocline creates a pattern of temperature fluctuation that they must adapt to, a daily rhythm of warming and cooling. The characteristics of thermoclines also vary by latitude, shaped by the different climate regimes from equator to poles. In the tropics, where sunlight is strong year-round and winds are often relatively calm, thermoclines tend to be shallow, strong, and permanent. Tropical waters might have a permanent thermocline starting at just 100 meters depth, with a seasonal thermocline layered above it at 30 or 40 meters, and on calm days even a diurnal thermocline in the topmost meter. The ocean is highly stratified, divided into distinct temperature zones with sharp boundaries between them. In temperate regions at middle latitudes, thermocline behavior is dominated by seasonal changes. Summer brings strong stratification with a pronounced seasonal thermocline. Winter brings deep mixing and weak or absent thermoclines. The permanent thermocline lies deeper in temperate waters than in the tropics, often starting at 200 meters or more, and it's somewhat less intense because the surface water doesn't get quite as warm as in equatorial regions. In polar regions, thermoclines are weak or non-existent. The water is cold from top to bottom, with little temperature variation with depth. There's simply not enough solar heating to create a warm surface layer, and the constant cold means the entire water column remains near freezing year-round. Arctic and Antarctic waters do show some stratification, but it's often driven more by salinity differences, by haloclines where fresh meltwater sits atop saltier seawater, than by temperature gradients. The absence of strong thermoclines in polar waters has important ecological consequences. Without stratification to trap nutrients in the depths, polar seas can be highly productive, with nutrients readily available throughout the water column. Understanding these different types and patterns of thermoclines reveals that the ocean is not a static body, but a dynamic, layered system constantly adjusting to changes in sunlight, wind, season, and location. The invisible boundaries shift and strengthen and weaken, creating a complex, ever-changing thermal landscape beneath the waves. When we think about the vertical structure of the ocean, it's helpful to visualize it as a three-layer cake, with each layer having distinct characteristics. At the top is the epipelagic zone, also called the sunlit zone, or the mixed layer. This is the ocean's surface realm, extending from the very top down to roughly 200 meters in clear tropical waters, though often much shallower in cloudier or more turbulent regions. The epipelagic zone is where sunlight penetrates sufficiently for photosynthesis to occur. It's the productive layer, where microscopic phytoplankton drift in the currents, converting sunlight and carbon dioxide into organic matter, forming the base of the ocean food web. The epipelagic zone is characterized by relatively warm temperatures, abundant light, and vigorous mixing from wind and waves. Temperatures here can range from tropical warmth of 28 or 30 degrees Celsius down to cold polar waters of -2 degrees, depending on latitude and season. The water is well oxygenated because it's in constant contact with the atmosphere, with waves and bubbles continually dissolving oxygen from the air into the water. Marine life is abundant and diverse in this layer. Schools of fish dart through the sunlit water, dolphins and whales surface to breathe. Seabirds dive from above to catch prey. This is the vibrant living surface of the sea, the realm we're most familiar with when we swim or sail or gaze at the ocean from shore. At the bottom of the epipelagic zone, typically between 100 and 200 meters depth in open ocean, we encounter the thermocline. This is not so much a layer as a boundary, a transition zone where conditions change rapidly. The thermocline marks the bottom of the mixed layer and the top of a very different world below. Within the thermocline, temperature drops sharply. Light fades significantly. The physical properties of the water change in ways that affect how sound travels, how nutrients are distributed, how dense the water is. The thermocline is a barrier, though not an impermeable one. Some organisms cross it regularly. Some water masses do mix across it, especially during storms or upwelling events. But it's a significant obstacle, a place where the easy exchange between surface and depth is impeded. Below the thermocline lies the mesopelagic zone, the twilight zone of the ocean. This layer extends from about 200 meters down to roughly 1,000 meters, though boundaries are fuzzy and variable. In the mesopelagic, light is dim, barely sufficient for vision and wholly insufficient for photosynthesis. The water here is cold, typically between 5 and 10 degrees Celsius in most parts of the ocean. Organisms that live in the mesopelagic have adapted to cold, dark conditions. Many are bioluminescent, producing their own light through chemical reactions. Many have large eyes to catch the faint downwelling light from above. Many migrate, swimming upward at night to feed in the richer epipelagic zone, then descending during the day to avoid predators. The mesopelagic is a zone of transition, still connected to the surface waters above through the daily vertical migrations of countless organisms, through the slow settling of organic particles, through the occasional mixing event that brings deeper water toward the surface. But it's fundamentally different from the sunlit zone, colder and darker and quieter. The thermocline separates these two realms, creating a boundary between the warm, bright, productive surface and the cold, dim, mysterious twilight below. Deeper still, below the mesopelagic, lies the bathypelagic or deep ocean zone, extending from roughly 1,000 meters down to the seafloor, which might be 4,000 or 5,000 meters deep or more in the abyssal plains. This is the realm of permanent cold and perpetual darkness. Temperatures here are typically just 2 to 4 degrees Celsius year-round. No sunlight penetrates this deep. Life is sparse and specialized, adapted to extreme pressure, total darkness, and scarce food resources. The deep ocean is the largest habitat on Earth by volume, yet it's one of the least explored and least understood. The transition from the mesopelagic to the bathypelagic occurs at the bottom of the main thermocline, where the last vestiges of temperature change give way to the isothermal conditions of the abyss. Below roughly 1,000 meters, temperature barely changes with depth. The water is uniformly cold all the way to the bottom. This is a thermal deep layer represents water masses that formed at the surface in polar regions, sank because of their cold density, and then spread through the deep ocean basins, isolated from the warmer surface waters by the thermocline far above. So the ocean's three-layer structure consists of a warm, mixed, productive surface zone, a sharp transition zone characterized by the thermocline, and a cold, stable, dark, deep zone. Each layer has its own ecology, its own physics, its own role in the ocean system, and the thermocline is the critical boundary that separates them, that keeps them distinct yet allows some exchange between them. The thermocline doesn't just organize water masses. It profoundly shapes the lives of marine organisms, influencing where they can live, how they behave, and what strategies they use to survive. For fish and other mobile marine creatures, the thermocline represents both an obstacle and an opportunity, a boundary they must navigate in their daily and seasonal lives. Many fish species have preferred temperature ranges within which they thrive. Their metabolism, their ability to digest food, their swimming performance, even their behavior all depend on being within their optimal temperature zone. When a fish swims through a thermocline, it experiences a rapid temperature change that can be physiologically challenging. Crossing from warm surface water into the cold water below the thermocline is like walking from a warm room into a refrigerator. It's a shock to the system. As a result, many fish choose to stay within particular temperature layers, either above or below the thermocline, avoiding the transition zone itself. This creates vertical zonation in fish communities. Different species occupy different depth ranges, based partly on their temperature preferences. Tuna and marlin, warm-bodied fish with high metabolic rates, tend to frequent the warm surface waters above the thermocline. They need the higher temperatures to support their energetic lifestyle of fast swimming and active hunting. Deeper-dwelling species like lanternfish and hatchetfish occupy the cooler waters of the mesopelagic zone below the thermocline. They're adapted to cold conditions and would be uncomfortable in the warm surface layer. But many fish don't simply stay put. They move vertically through the water column, crossing thermoclines regularly as part of daily migration patterns. This phenomenon, called diel vertical migration, is one of the most widespread animal behaviors on Earth and one of the largest movements of biomass on the planet. Every evening as the sun sets, countless billions of small fish, squid, krill, and other zooplankton rise from the depths toward the surface. They cross the thermocline, swimming from the cold mesopelagic into the warmer epipelagic zone to feed on phytoplankton and smaller zooplankton that concentrate near the surface. Then, before dawn, they descend again, crossing back through the thermocline to spend the daylight hours in the dim safety of the deeper water. This daily migration is thought to be driven primarily by predator avoidance, by feeding at night and hiding in the depths during the day. These organisms reduce their risk of being eaten by visual predators that hunt in daylight. But crossing the thermocline twice a day comes at an energetic cost. The The animals must swim vertically through hundreds of meters of water, experiencing significant temperature changes and pressure changes along the way. For them, the thermocline is not an impassable barrier, but a regular feature of their daily commute, a boundary they cross with regularity. The thermocline also affects fish behavior by influencing the distribution of prey. In stratified waters, nutrients tend to be trapped below the thermocline. During summer, when the seasonal thermocline is strong, nutrients in surface waters get used up by phytoplankton. Without mixing from below to replenish them, surface waters can become nutrient depleted, limiting phytoplankton growth. Meanwhile, below the thermocline, nutrients may be abundant but unused because there's not enough light for photosynthesis. This creates a situation where food resources are concentrated at certain depths, often just above or just below the thermocline, where some mixing still occurs or where sinking particles accumulate. Predatory fish know this and adjust their behavior accordingly. Many species hunt at specific depths where prey is concentrated, depths often defined by the thermocline's location. Fishermen have learned to target these depths as well, using fish finders that can detect the thermocline as a distinct horizontal line on their sonar screens, knowing that fish often congregate near this boundary. The thermocline becomes a kind of underwater landmark, a reference point for finding fish. Oxygen availability also plays a role in how thermoclines affect marine life. The thermocline limits vertical mixing, and this has consequences for oxygen distribution. In the epipelagic zone, oxygen is abundant. The water is in contact with the atmosphere, and photosynthesis by phytoplankton produces additional oxygen during daylight. But below the thermocline, oxygen can become scarce. No photosynthesis occurs in the darkness of the mesopelagic, and the thermocline prevents oxygen-rich surface water from mixing downward. Meanwhile, the bacteria and animals in deeper water continue consuming oxygen as they respire. The result can be an oxygen minimum zone, a layer often found just below the thermocline where oxygen concentrations drop to very low levels. For fish and other organisms, the oxygen minimum zone can be a physiological barrier. Most fish require relatively high oxygen levels to support their active lifestyle. In regions where the oxygen minimum is severe, it creates a squeeze. Fish need to stay above the thermocline to access sufficient oxygen, but they may also be drawn below it to find preferred temperatures or prey. Some species have adapted to tolerate low oxygen, developing large gills or altered blood chemistry that allows them to extract what little oxygen is available. But for many, the oxygen minimum zone associated with the thermocline is a no-go area, a layer they simply cannot inhabit. Marine mammals, too, interact with thermoclines in their diving behavior. Whales and dolphins diving deep must pass through the thermocline. They experience the temperature change as they descend from warm surface water into cold deep water. Some species may adjust their diving patterns based on thermocline depth. Sperm whales, which dive to great depths to hunt squid, regularly pass through multiple thermoclines on their way down and back up. The temperature shock might be minimized by their thick blubber layer, which provides insulation, and by the fact that they spend most of their lives in water anyway. Their bodies adapted to thermal fluctuations. Smaller organisms, too, feel the effects of thermoclines. Jellyfish and other drifting animals may accumulate at thermocline depths, forming concentrated layers. Some species of jellyfish appear to use the thermocline as a kind of platform, hovering at the boundary between warm and cold water. Plankton distributions often show peaks in abundance at thermocline depths, creating thin layers of concentrated organisms just a meter or two thick but extending horizontally for kilometers. These thin layers are thought to form because of the stable conditions at the thermocline where organisms can aggregate without being dispersed by turbulent mixing. So the thermocline is far more than just a temperature boundary. It's an ecological boundary, structuring where organisms live, how they move, and how they interact with each other. It divides the ocean, not just physically, but biologically, creating distinct habitats above and below, separated by an invisible yet profoundly important transition zone. The thermocline's influence changes with the rhythm of the seasons, particularly in temperate waters where seasonal contrasts are pronounced. Understanding the seasonal cycle of thermocline formation and breakdown helps us appreciate how the ocean transitions between different states throughout the year, and how marine ecosystems respond to these changes. In winter, in temperate and high-latitude oceans, the sea surface cools considerably. Air temperatures drop. sometimes falling below water temperatures. The ocean begins to lose heat to the cold air above through processes of evaporation and direct heat transfer. As the surface water cools, it becomes denser and sinks, replaced by slightly warmer water from below. This process, called convective overturning, mixes the upper ocean deeply. Storm systems are frequent in winter, with strong winds that further enhance mixing. The combined effects of cooling and wind mixing can create a mixed layer several hundred meters deep, extending far deeper than the summer mixed layer. During winter, the seasonal thermocline disappears entirely in many temperate regions. The water column becomes nearly isothermal down to considerable depths, with only the permanent thermocline, if present, maintaining a temperature difference between the surface layer and the truly deep water. This deep winter mixing has important ecological consequences. Nutrients that were trapped below the thermocline during summer are now mixed upward, brought back into the sunlit zone where phytoplankton can use them. The winter ocean, though cold and stormy, is being fertilized, prepared for the burst of productivity that will come with spring. As winter transitions to spring, days lengthen and the sun climbs higher in the sky. Solar radiation increases and the ocean surface begins to warm. At first, the warming is spread through the deep mixed layer by continued wind mixing, and the entire mixed layer warms gradually. But eventually, a threshold is crossed. The surface water warms enough and the winds calm sufficiently that a shallow thermocline begins to form. This spring thermocline is initially weak and variable, easily disrupted by passing storms. But as spring progresses towards summer, it strengthens and shallows, becoming a more persistent feature. The formation of the spring thermocline coincides with the spring phytoplankton bloom, one of the great seasonal events of temperate oceans, with longer days providing more light, with nutrients abundant from winter mixing, and with the water beginning to stratify, conditions become ideal for phytoplankton growth. Microscopic algae multiply rapidly, turning the water greenish with their high concentrations. Zooplankton graze on the phytoplankton, and fish come to feed on the zooplankton. The spring bloom is a time of plenty, a seasonal explosion of life that ripples through the food web. But the spring thermocline also begins to limit the bloom. As stratification increases, nutrients in surface waters get used up, and the thermocline prevents them from being replenished from below. The bloom peaks and then declines, with phytoplankton populations dropping as nutrients become scarce. By late spring, surface waters may be relatively clear, nutrient depleted, with most biological activity concentrated near the thermocline depth, where some mixing still occurs, or where nutrients remain available. Summer brings the strongest stratification of the year in temperate oceans. The surface layer warms to its maximum temperatures, often 15 to 20 degrees Celsius or more. The seasonal thermocline is sharp and shallow, perhaps at 10 to 30 meters depth. Below it, the water remains much cooler. The temperature difference between surface and thermocline layer can exceed 10 degrees Celsius. This creates a stable, stratified water column, one of the most resistant to mixing of any time of year. During summer, multiple thermoclines can coexist. The seasonal thermocline sits above the permanent thermocline, and on calm days, a diurnal thermocline may form in the topmost meter or two. The ocean becomes layered, terraced, with step-like temperature changes at different depths. This stratification has both benefits and drawbacks for marine life. The warm surface water is comfortable for warm water species and supports high metabolic rates, but the lack of mixing means nutrients are scarce in surface waters, limiting productivity. The thermocline acts as a barrier, isolating surface waters from the nutrient-rich depths. Phytoplankton in summer surface waters may be light-limited, not by lack of sunlight, which is abundant, but by lack of nutrients. They can't grow much because they've exhausted the available nitrogen and phosphorus in the warm, stratified surface layer. Some species adapt by positioning themselves at the thermocline depth, where enough light penetrates for photosynthesis, and where some nutrients may still be available from below. These deep chlorophyll maxima, layers of phytoplankton concentrated at depth, are common features of stratified summer oceans. As autumn approaches, the cycle reverses. Days shorten and solar heating diminishes. The air cools more quickly than the ocean, and eventually the atmosphere becomes cooler than the sea surface. Now the ocean begins to lose heat, giving up its stored summer warmth to the air. The surface water cools, becomes denser, and sinks, initiating the fall overturn. the seasonal thermocline begins to break down as the surface layer mixes deeper and deeper. Fall storms accelerate this process. Strong winds churn the surface, breaking down stratification and mixing the water column. Nutrients that were locked below the thermocline during summer are brought back to the surface. In some regions, this can trigger a secondary phytoplankton bloom, a fall bloom smaller than the spring event but still significant. As fall progresses into winter, the mixing continues until once again the seasonal thermocline disappears entirely, the cycle completing and preparing to begin anew with the next spring. This seasonal rhythm of thermocline formation and destruction is one of the fundamental patterns structuring temperate ocean ecosystems. It drives seasonal changes in productivity and nutrient availability in species distributions. It means the ocean is very different in summer than in winter, not just in temperature but in its entire physical and biological structure. And it's all orchestrated by the interplay of sunlight, wind, and the thermocline's response to these forcing factors. The thermocline isn't just important for marine life and ocean physics. It has played a crucial role in naval warfare, particularly in submarine operations, because of how it affects the propagation of sound through seawater. Understanding this connection takes us into the realm of underwater acoustics and the cat and mouse games that submarines and submarine hunters have played for over a century. Sound is the primary means of detecting objects underwater. Light doesn't penetrate far in the ocean, and electromagnetic waves like radio are quickly absorbed by seawater. But sound travels well through water, much better than through air. Sound waves can travel for kilometers or even tens of kilometers through the sea, making sonar, sound navigation and ranging the tool of choice for finding submarines and other underwater objects. However, sound doesn't travel in straight lines through the ocean. It bends or refracts when it passes through water of different densities, and density in seawater is primarily controlled by temperature. This is where the thermocline becomes critically important. The thermocline is a region of rapidly changing temperature, and therefore rapidly changing density, and this affects sound propagation in ways that submarines can exploit and submarine hunters must account for. Sound waves travel faster in warm water than in cold water. When a sound wave passes from warm surface water into the colder water below the thermocline, it slows down. According to the principles of refraction, when a wave slows down, it bends. In the case of sound crossing a thermocline from above, the sound wave bends downward away from the surface. This means that if a ship on the surface is using sonar to search for a submarine, and the submarine is below the thermocline, the sound waves from the sonar may bend away from the submarine, missing it entirely. The submarine becomes acoustically hidden, shielded by the thermocline from detection from above. This creates what's called an acoustic shadow zone. Below the thermocline, there's a region where sound from surface sources can't easily penetrate. A submarine hiding in this shadow zone is essentially invisible to many types of active sonar coming from surface vessels. The thermocline acts as an acoustic mirror of sorts, reflecting or refracting sound waves away from the depths, creating a sheltered layer where submarines can lurk undetected. Naval forces discovered this effect during the early 20th century, particularly during World War I, when anti-submarine warfare became a critical concern. Sonar was a new technology at the time, and operators found that submarines sometimes disappeared from their sonar screens, despite being nearby. Investigation revealed that the submarines had dived below the thermocline, entering the acoustic shadow where they couldn't be detected. This led to the development of bathythermographs, instruments that could measure the temperature profile of the water column and predict where thermoclines would be. Knowing the thermocline's depth allowed submarine hunters to deploy sonar systems at the right depth to overcome the acoustic barrier. Submarines learned to use thermoclines tactically. A submarine captain facing pursuit might dive below the thermocline, using the acoustic shadow to evade detection. The submarine would run quietly at depth, below the thermal boundary, while sonar pings from surface ships passed overhead, unable to penetrate into the shadow zone below. This tactic was featured in numerous submarine warfare scenarios during World War II and the Cold War. Submarine crews were trained to understand thermoclines, to recognize them in temperature profiles, and to use them for concealment. The effect works in both directions. A submarine below the thermocline has difficulty hearing targets above it, for the same reason that targets above can't easily detect the submarine. Sound from above bends away as it crosses the thermocline. Similarly, sound generated by the submarine may be trapped below the thermocline, unable to reach the surface. This creates tactical trade-offs. Hiding below the thermocline provides concealment but also limits the submarine's ability to detect surface targets. To overcome the thermocline's effects, navies developed various strategies. Variable depth sonar, towed behind ships on long cables, can be lowered below the thermocline to detect submarines in the acoustic shadow. Sonobores, small floating devices dropped from aircraft, can deploy hydrophones at various depths to listen for submarines both above and below the thermocline. Modern submarines also use towed arrays, long cables trailing behind the sub equipped with sensitive hydrophones that can detect faint sounds from great distances, even across thermocline boundaries. The thermocline's acoustic effects are most pronounced in tropical and subtropical waters where strong, shallow thermoclines create intense acoustic barriers. In these regions, submarine tactics heavily involve diving below the thermocline to evade detection. In polar waters where thermoclines are weak or absent, the acoustic environment is different, with fewer opportunities for acoustic concealment based on temperature layering. The physics of sound refraction at thermoclines is complex. The exact behavior depends on the strength of the thermocline, its depth, the frequency of the sound waves, and the angle at which the sound approaches the boundary. Low-frequency sound refracts differently than high-frequency sound. Sound traveling horizontally along the thermocline behaves differently than sound traveling vertically through it. Understanding all these factors requires detailed knowledge of the ocean's temperature structure, which is why oceanography and naval operations have been so closely linked for the past century. Beyond tactical submarine operations, thermoclines affect other acoustic phenomena in the ocean. They influence how whale songs propagate, how underwater earthquakes are detected, how ships' engines are heard from far away. The ocean is a sonic landscape shaped by temperature boundaries, and the thermocline is one of the most important features of that landscape, an invisible layer that channels, reflects, and distorts the sounds that fill the sea. The thermocline that shapes today's oceans is itself being shaped by human-induced climate change. As the planet warms, the ocean absorbs much of that excess heat, and this has profound effects on thermocline characteristics. Understanding how thermoclines are changing helps us grasp the broader impacts of warming on ocean systems and the life they support. Ocean warming doesn't happen uniformly throughout the water column. The surface ocean, in contact with the warming atmosphere and absorbing increased solar radiation, warms faster than the deep ocean. Deep water is relatively insulated from surface conditions, changing slowly over decades and centuries as new deep water forms in polar regions. This differential warming, surface heating faster than deep water, means that the temperature difference between the epipelagic zone and the deep ocean is increasing. The thermocline is becoming stronger, the temperature gradient steeper. A stronger thermocline means greater stratification. Warm, light water at the surface becomes even lighter as it warms, making it less likely to mix downward. The barrier between surface and deep water becomes more resistant to vertical mixing. This increased stratification has several important consequences. First, it reduces the exchange of nutrients between surface and depth. Nutrients in deep water, which might have mixed upward during storms or other mixing events, are now more likely to stay below the thermocline. Surface waters may become increasingly nutrient-limited, reducing ocean productivity in some regions. Second, increased stratification limits the downward mixing of oxygen. Surface waters remain well oxygenated through contact with the atmosphere, but below the thermocline, oxygen levels may decline as organisms consume it, and no new oxygen is supplied from above. This can expand oxygen minimum zones, creating larger areas of water that are uninhabitable for most marine life. Fish and other animals may be squeezed into narrower vertical ranges, trapped between the warm surface they cannot tolerate and the oxygen-poor depths they cannot survive in. Third, enhanced stratification affects the ocean's ability to absorb carbon dioxide from the atmosphere. The ocean is a major sink for atmospheric CO2, absorbing about a quarter of the carbon dioxide emitted by human activities. But this absorption depends on oceanic circulation that brings surface water into the deep ocean where the dissolved CO2 can be stored for centuries. If increased stratification reduces this circulation, reduces the rate at which surface water mixes downward, then the ocean's capacity to absorb CO2 may diminish. This would create a feedback loop, with more CO2 remaining in the atmosphere, causing more warming, causing more stratification, further reducing CO2 absorption. Observations from around the world's oceans show that stratification has indeed been increasing over recent decades. Measurements of temperature profiles reveal that the thermocline has been strengthening, that the mixed layer has been becoming shallower, that the difference between surface and deep water temperatures has been growing. These changes are consistent with climate model predictions and with the physics of a warming ocean. The depth of the thermocline is also changing in many regions. In some areas, the thermocline is deepening as surface waters warm and the mixed layer depth increases. In other areas, it's shallowing as increased stratification confines warming to the very uppermost layer. These changes vary by region and season, creating a complex global pattern. But the overall trend towards stronger stratification appears to be widespread. Marine ecosystems are responding to these changes. Species distributions are shifting as organisms track their preferred temperature ranges. Fish that once thrived in certain areas may move poleward or to deeper waters as surface temperatures rise. Coral reefs, which exist in a narrow temperature range, are experiencing increased bleaching events when surface temperatures exceed their tolerance. Phytoplankton productivity is changing, with some regions showing increases where nutrients become more available, and others showing decreases where stratification limits nutrient supply. The changing thermocline also has implications for hurricanes and tropical cyclones. These storms draw their energy from warm surface water. A deeper thermocline means a deeper reservoir of warm water that storms can tap into, potentially making them stronger. Hurricane forecasters now routinely consider not just sea surface temperature but also the depth of the thermocline, the thickness of the warm layer above it when predicting storm intensity. A hurricane passing over water with a shallow thermocline may quickly exhaust the warm surface water, mixing cooler water from below and weakening. But a storm over water with a deep thermocline can maintain its intensity longer. Scientists study thermocline changes using various methods. Ships equipped with instruments called CTDs, conductivity temperature depth probes, can measure detailed temperature profiles. Autonomous floats called Argo floats drift through the ocean, diving periodically to measure temperature and salinity at depth, then surfacing to transmit data via satellite. Thousands of these floats now provide a global monitoring network. Satellites measure sea surface temperature from space, though they can't see below the surface. Together, these observations build a picture of how the thermocline is changing over time. The changes to thermoclines are part of a broader transformation of the ocean under climate change. The ocean is warming, becoming more acidic as it absorbs CO2, losing oxygen, changing its circulation patterns. The thermocline is both a player in these changes and an indicator of them. By understanding how thermoclines respond to warming, scientists gain insights into the future of ocean systems and the marine life that depends on them. The invisible nature of thermoclines doesn't mean they can't be detected or experienced. Divers, in particular, have long been familiar with the sensation of swimming through a thermocline, and modern technology provides multiple ways to visualize these temperature boundaries. For a scuba diver descending through a thermocline, the experience is unmistakable. Swimming in the warm surface water, comfortable in a thin wetsuit or perhaps even just swim trunks in tropical seas, the diver suddenly encounters cold. It's not a gradual cooling but an abrupt change, as if passing through an invisible curtain. Within a meter or two of descent, the temperature might drop 5 or 6 degrees Celsius. It's a shock, a reminder that the ocean is layered, that different worlds exist at different depths. The visual appearance of a thermocline is equally distinctive. As a diver approaches the boundary, the water below often appears blurred or wavy, similar to heat shimmer seen rising from hot pavement on a summer day. This visual distortion is caused by the difference in refractive index between the warm water above and cold water below. Light bends as it crosses the thermocline, just as sound does, creating the blurry, shimmering effect. Divers describe it as looking through frosted glass or through the air above a candle flame. The thermocline becomes visible not as a physical object, but as a distortion, a wavering layer where the water seems to ripple even though it's still. Once through the thermocline, a diver enters a noticeably different environment. The water is colder, often clearer, because it's below the productive surface layer. The light is different, more blue-shifted as the warmer colors of the spectrum have been absorbed by the water above. Visibility might improve or worsen depending on particulates in the water. The thermocline acts as a boundary between realms, and crossing it is a transition into another aspect of the ocean. Scientists and oceanographers detect thermoclines using specialized instruments. The bathy thermograph mentioned earlier was an early device that recorded temperature versus depth on a mechanical chart. Modern instruments are electronic. A CTD probe can measure temperature continuously as it's lowered through the water, producing a precise temperature profile that shows the thermocline as a steep slope in the temperature depth curve. Expendable bathy thermographs, XBTs, are small probes that can be dropped from ships and aircraft, measuring temperature as they fall and transmitting data via a thin wire before the wire breaks and the probe is abandoned in the deep. Fish finders sonar devices used by anglers can detect thermoclines as distinct horizontal lines on their displays. The thermocline shows up because of the change in water density, which affects how sound reflects. A fish finder sends sonar pulses downward and listens for echoes. When the pulse encounters the density change at the thermocline, some of the sound is reflected back, creating a return signal that appears as a line on the display. Experienced anglers learn to recognize thermocline signatures on their fish finders and use this information to target depths where fish are likely to be found. Satellites can measure sea surface temperature from space using infrared sensors, but they can only see the very surface, the skin of the ocean. They can't directly detect thermoclines beneath. However, satellite measurements combined with computer models allow scientists to infer thermocline depths based on surface temperature patterns and known relationships between surface conditions and subsurface structure. Oceanographic research vessels conduct regular surveys, lowering instruments through the water column to measure temperature, salinity, oxygen, and other properties at many depths. These profiles reveal the structure of thermoclines, their depth, strength, and variability. Over time, repeated surveys at the same locations allow scientists to track how thermoclines change seasonally and over longer timescales. The accumulated data from all these sources, ships and floats and satellites and historical records, create a global picture of thermocline structure. Oceanographers can produce maps showing where thermoclines are shallow or deep, strong or weak. They can identify regions where the thermocline is highly variable, changing dramatically from season to season, and regions where it's relatively stable. This knowledge is essential for understanding ocean circulation, for predicting marine ecosystem dynamics, for forecasting weather and climate. The ability to detect and measure thermoclines has transformed our understanding of the ocean. What was once an invisible, mysterious boundary is now a well-mapped, intensively studied feature. Yet even with all our instruments and data, there's something humbling about the thermocline's invisibility. It reminds us that the ocean holds structure we cannot see with our eyes, that temperature and density create invisible architecture as real and important as any visible reef or canyon. Thermoclines are not unique to the ocean. Lakes, too, develop temperature layering, and understanding lake thermoclines reveals both the universality of thermal stratification and the differences between oceanic and freshwater systems. Lakes stratify in response to seasonal heating and cooling, just as oceans do. But lakes are smaller, shallower, and more isolated than ocean basins, and this creates different patterns. In temperate regions, lakes go through a seasonal cycle of stratification and mixing that's particularly pronounced. During summer, a typical temperate lake becomes stratified into 3 layers. The surface layer, called the epilimion, is warm and well mixed by wind. Below it lies the metalimion, or thermocline, where temperature drops rapidly. The bottom layer, the hyperimion, is cold and relatively still. This structure is similar to the ocean's stratification, with a warm mixed layer above a thermocline above a cold deep layer. The summer thermocline in a lake can be very strong, with temperature differences of 10 degrees Celsius or more occurring over just a few meters of depth. The depth of the thermocline varies depending on lake size and wind exposure. Shallow lakes may have thermoclines just a few meters down. Large, deep lakes can have thermoclines at 10 or 20 meters or deeper. Wind mixing determines how deep the epilimion extends. Stronger winds drive deeper mixing and push the thermocline deeper. Lake thermoclines have important consequences for water quality and aquatic life. Below the thermocline in the hypolimnion, oxygen levels often decline over the course of summer. Bacteria decomposing organic matter on the lake bottom consume oxygen, and with no mixing from above to replenish it, the hypolimnion can become anoxic, devoid of oxygen. Fish and other organisms cannot survive in the anoxic hypolimnion, so they're confined to the epilimion and perhaps the thermocline region. In extreme cases, this can lead to fish kills if the oxygenated zone becomes too small or too warm to support the fish population. As autumn arrives, the lake surface cools. Eventually, the epilimnion cools to the same temperature as the hypolimnion. At this point, the lake undergoes fall turnover. The thermocline disappears as the entire lake mixes from top to bottom. Winds can now circulate water throughout the full depth, because there's no density difference to resist mixing. Oxygen is redistributed, nutrients from the bottom are brought to the surface, and the lake becomes well mixed and uniform in temperature. Winter brings further changes. As the surface continues to cool, the water temperature drops toward freezing. Here, something unusual happens. Water has its maximum density at 4 degrees Celsius. As water cools below 4 degrees, it actually becomes less dense. This means that when a lake cools in winter, the coldest water, approaching 0 degrees, is less dense than the slightly warmer water at 4 degrees and rises to the surface. The densest water, at 4 degrees, sinks to the bottom. This creates an inverse thermocline, with cold water at the surface and warmer, denser water at depth. If the lake freezes, ice forms on the surface, insulating the water below. The lake remains stratified throughout winter, with ice at 0 degrees at the top, water just above 0 below the ice, and water at 4 degrees at the very bottom. This winter stratification protects aquatic life. Even though the surface is frozen, fish and other organisms can survive in the liquid water below, which remains above freezing. When spring arrives and ice melts, the surface water warms toward 4 degrees. At this point, the entire lake can reach 4 degrees. The temperature of maximum density and spring turnover occurs, like fall turnover. This is a period of complete mixing. Once spring turnover is complete and surface warming continues, the summer thermocline begins to form again, and the cycle repeats. This seasonal cycle of stratification in temperate lakes is one of the fundamental patterns of freshwater ecology. It dictates when nutrients are available, when oxygen can reach the depths, when different parts of the lake are habitable. Lake organisms have adapted their life cycles to this rhythm. Some aquatic insects time their reproduction to coincide with turnover events. Fish spawn in different seasons depending partly on temperature and oxygen conditions set by the thermocline cycle. Tropical lakes behave differently. In warm climates, surface water stays warm year-round, and deep water remains cold. The thermocline in tropical lakes can be a permanent feature, never breaking down because the surface never cools enough to match the deep water temperature. These permanently stratified lakes can develop anoxic deep layers that persist for years, becoming inhospitable zones cut off from oxygen and light. High-altitude lakes in tropical regions sometimes experience daily mixing despite warm climates. Cool nights allow surface cooling and mixing, while warm days re-establish stratification. These lakes may go through a daily cycle of weak stratification and mixing rather than a seasonal cycle. Arctic and alpine lakes may be ice-covered for much of the year, with only brief periods of stratification during short summers. The thermocline in these lakes is a temporary summer feature, quickly established when the ice melts and just as quickly destroyed when fall cooling begins. Lake thermoclines are important for lake management. Drinking water reservoirs must be managed to maintain water quality, which means understanding stratification patterns and preventing the development of anoxic conditions. Fish hatcheries and aquaculture operations must account for thermoclines when stocking fish or managing populations. Even recreational use of lakes is affected. Swimmers and boaters may encounter thermoclines, and anglers target specific depths based on where the thermocline is located. The study of lake thermoclines has paralleled the study of oceanic thermoclines, with many of the same principles applying but with the additional complexity of seasonal ice cover and the unique properties of freshwater. Together, ocean and lake studies reveal that thermal stratification is a fundamental characteristic of water bodies, a natural consequence of how water responds to heating, cooling, and wind mixing. The thermocline acts as a barrier to vertical mixing, and this has profound implications for nutrient cycling and the biological productivity of the ocean. Understanding this connection reveals why some parts of the ocean are rich with life, while others are relatively barren, and why the thermocline is so crucial to marine ecosystems. Nutrients, the chemical building blocks of life, include elements like nitrogen, phosphorus, and iron that phytoplankton need to grow. These nutrients are introduced to the ocean through various pathways: Rivers bring them from land, atmospheric dust deposits them on the surface, and deep water brings them up from the seafloor where they've accumulated over time. But in the open ocean, away from coastal inputs, the main source of nutrients for surface waters is upward mixing from the depths. Deep ocean water is typically nutrient-rich, as organic matter sinks from the surface, from the remains of dead phytoplankton and zooplankton and larger organisms. It settles into the deep layers where bacteria decompose it, releasing nutrients back into the water. Over time, nutrients accumulate in the deep ocean while being depleted in surface waters where phytoplankton use them. This creates a situation where the deep ocean is a reservoir of nutrients, but those nutrients are only useful if they can reach the sunlit zone where photosynthesis occurs. The thermocline acts as a barrier to this upward transport. Its strong density gradient resists vertical mixing. Water below the thermocline is denser and wants to stay below. Water above the thermocline is lighter and stays above. Without some force to break down this stratification, nutrients in the deep remain there, inaccessible to surface phytoplankton. During stratified conditions, typically summer in temperate regions or year-round in the tropics, surface waters become nutrient-limited. Phytoplankton use up the available nutrients, and without replenishment from below, their growth slows or stops. This limits the productivity of the entire ecosystem because phytoplankton are the base of the food web. Fewer phytoplankton means less food for zooplankton, which means less food for fish and so on up the chain. The surface ocean can become an azure desert, beautiful but biologically sparse, because nutrients are locked below the thermocline. The thermocline's barrier is not absolute. Some mixing does occur. Internal waves, underwater currents that oscillate along the thermocline, can cause pulses of upward mixing. Storms can temporarily break down stratification, especially at the thermocline's upper boundary, allowing some nutrient injection. Upwelling currents driven by winds or ocean circulation can bring deep, nutrient-rich water to the surface in certain regions, bypassing the thermocline's barrier. But in most of the open ocean, most of the time, the thermocline effectively isolates surface and deep waters. This is why upwelling zones are so productive. Along certain coastlines, winds blow surface water offshore, and deep water rises to replace it. This upwelled water is cold and nutrient-rich, having come from below the thermocline, where upwelling occurs. Phytoplankton thrive, supporting rich food webs and massive fish populations. The great fishing grounds of the world, places like the California Current, the Humboldt Current off Peru, and the Benguela Current off Southwest Africa, are all upwelling zones where the thermocline's barrier is overcome by large-scale ocean circulation. Phytoplankton have adapted to the thermocline's barrier in various ways. Some species can adjust their buoyancy, sinking at night to depths where nutrients are more available, then rising during the day to the sunlit zone to photosynthesize. Others form dense concentrations right at the thermocline depth, positioning themselves at the boundary where sunlight penetrates from above and some nutrients diffuse from below. These deep chlorophyll maxima are common features of stratified oceans, layers of phytoplankton living in the dim light just above or within the thermocline. The seasonal breakdown of the thermocline has enormous ecological importance precisely because it relieves nutrient limitation. When the thermocline disappears during winter mixing, nutrients from depth are brought back to the surface. This sets the stage for the spring bloom. As soon as days lengthen and light increases, phytoplankton can explode in abundance because both light and nutrients are available. The spring bloom is often the most productive period of the year in temperate oceans, a time when phytoplankton densities increase 100-fold and the entire food web responds. The timing of thermocline breakdown affects the timing of the spring bloom. If winter mixing is weak, if the thermocline doesn't fully disappear, then nutrient replenishment is limited and the subsequent bloom may be small. If mixing is vigorous and deep, nutrients are abundant and the bloom can be spectacular. Climate change, by altering wind patterns and surface temperatures, may be changing the timing and intensity of thermocline breakdown, with cascading effects on seasonal productivity cycles. Oxygen dynamics are also linked to the thermocline's barrier function. Below the thermocline, oxygen is consumed by organisms and by the bacterial decomposition of organic matter. Without mixing from above, oxygen is not replenished. In regions with high productivity and strong thermoclines, oxygen minimum zones develop, layers where oxygen concentrations drop to near zero. These zones are inhospitable to most fish and other mobile animals, creating a habitat squeeze where organisms are confined to the narrow zone between the warm, oxygenated surface and the anoxic waters below. So the thermocline is a key regulator of ocean fertility. By controlling the exchange of nutrients and oxygen between surface and depth, it shapes where and when the ocean is productive, where food webs flourish, and where biological deserts persist. It's an invisible hand shaping life in the sea. As we drift toward the end of our journey through the invisible boundaries of the ocean, let's return to the sense of wonder that the thermocline inspires. Here is a feature of Earth's oceans that we cannot see with our eyes, that leaves no visible trace on the surface, yet shapes countless aspects of the marine world. It divides the ocean into layers as surely as floors divide a building into stories. It influences everything from the smallest plankton to the largest whales, from ancient submarine tactics to modern climate change responses. The thermocline reminds us that the ocean is not a simple, uniform body of water, but a complex, structured, dynamic system. It's organized by invisible forces, by temperature and density, and the interplay of sunlight and wind. The thermocline is part of that organization, part of the hidden architecture that makes the ocean what it is. Understanding thermoclines gives us a deeper appreciation for the ocean's subtlety and complexity. It shows us that some of the most important boundaries in nature are not visible walls or edges, but gradients, transitions, zones where one condition gives way to another. The thermocline is such a transition, sharp yet continuous, invisible yet profoundly real in its effects. There is much we still don't know about thermoclines. How exactly will they respond to continued climate warming? Will increased stratification fundamentally change ocean ecosystems, shifting them toward new states we haven't seen before? How do marine organisms perceive and respond to these thermal boundaries? What role do small-scale processes, turbulence and mixing at scales too small to measure directly, play in determining how permeable the thermocline is? Scientists continue to study thermoclines using ever more sophisticated tools. Autonomous underwater vehicles can profile the water column repeatedly, building detailed pictures of how thermoclines change hour by hour. Computer models can simulate thermocline dynamics, testing hypotheses about what drives their behavior. Long-term monitoring programs track changes over years and decades, documenting the ocean's slow response to a changing climate. But for all the scientific study, there remains something almost poetic about the thermocline. It's a hidden layer, a secret the ocean keeps just beneath its sparkling surface. It's a reminder that the world contains structure we cannot see, boundaries that exist not as physical barriers but as gradients in temperature, as differences in density, as invisible yet consequential divisions. Tonight as you rest, the ocean's thermoclines are still there, still separating warm from cold, still shaping where fish swim and how sound travels, and where nutrients can reach the sunlit zone. They persist through day and night, through seasons and years, invisible yet essential features of the blue planet we call home. In tropical waters, the thermocline is sharp and permanent, a steep thermal cliff just 100 meters down. In temperate seas, it comes and goes with the seasons, forming in spring, strengthening through summer, disappearing in fall and winter only to return again. In polar regions, it barely exists, the water cold from surface to seafloor. Yet everywhere, the thermocline or its absence shapes the character of the sea. The next time you stand beside the ocean, or swim in its waters, or simply think about the vast blue that covers most of our planet, remember the thermocline. Remember that beneath the visible surface lies invisible structure. Remember that temperature draws boundaries in the water as real as any coastline. Remember that the ocean is layered, organized, divided into zones by forces we can measure but not see. The thermocline is part of that hidden order, one of the ocean's many secrets, revealed not to the eye but to the thermometer, to the diver who feels the sudden cold, to the scientist who interprets the data, to anyone who pauses to wonder about what lies beneath. As your mind drifts now towards sleep, let yourself imagine descending slowly through clear tropical water. The surface is warm, sun-dappled, comfortable, fish dart in the blue. Light filters down in shimmering columns. You descend slowly, peacefully, watching the light dim subtly as you go deeper. And then at perhaps 20 meters down, you feel it, the sudden coolness, not gradual, but abrupt. You've crossed the thermocline, passed through an invisible boundary into a different layer of the sea. Below you, the water stretches down into deeper blue, colder, calmer, another realm entirely. Above the warm, bright surface layer, another world. And here you are, suspended at the boundary between them, at the thermocline, the ocean's invisible border of warm and cold. Rest now, let the ocean's layers support you. Let the gentle physics of temperature and density hold you. Let the thermocline be just another of the beautiful, mysterious patterns that structure this water world we're so fortunate to explore. The ocean continues, warm above, cold below, layered and complex and endlessly fascinating. And you can rest, knowing that even as you sleep, these invisible boundaries persist, organizing the seas, shaping life, dividing and connecting the waters of our blue planet. Sleep well, dream softly. The thermocline endures, silent and invisible, in the depths of the world's oceans,